So, welcome to this month's ICG talk by Przemyslaw Musialski. He's an assistant
University assistant still, yeah.
at TU Vienna and a principal investigator at TU Vienna at the Institute of Discrete Mathematics and Geometry. We met at Bauhaus University a long time ago.
Exactly.
In a PhD student.
No, a master student actually.
And you did your PhD later on at TU.
At TU, yeah.
And from there, you have been at IRIS for a couple of years.
3 years.
At
Yes.
Arizona State.
Arizona State for 1.5 years. As a postdoc.
And you're going to talk about optimization or shape optimization for consumer level digital fabrication.
Exactly. So, thank you for the introduction. Thank you for the invitation. Actually, so I'm going to talk about shaped optimization, and I added this additional subscript consumer level because we are aiming partially at that level. So let me start with some motivation. So computer graphics is a lot about geometry, about modeling and geometry processing as well. However, usually the geometry is stays in a computer in most applications like games, animation, and so on and so forth. And nonetheless, nowadays the goal is also to fabricate objects, to create geometry which has some particular physical copy using, for example, 3D printing or other digital fabrication devices. And the problem is, so what happens when we just 3D print objects, model it geometrically, like this fish? So either it will sink or it will float on the surface because we haven't taken its physical properties into account usually. We just printed geometry. So the third option would be, for example, to have a fish in a well-controlled manner, which floats beneath the surface in a well-defined orientation. And this is actually the goal of our shape optimization project. And now I'm going to introduce you a little bit more step by step. So our goals are to optimize the shape such that it fulfills the desired goals, fulfills some properties like floating. On the other hand, we want to preserve the original shape because usually it's designed by a designer who would like to have it in the state he or she have created it. And the third goal is to have a method which is fast as possible, maybe even interactive. So let's have a look into a little bit more details. So the classical shape representation is a polygonal mesh. This is also what we use. So the input to our work, to our framework, to our algorithm is a triangular mesh. Now for simplification, let's have a look at it as the silhouette. So we denote it now as an input surface S, and the output of the algorithm are two surfaces, the outer surface, which we call as overline, and an inner surface, which we call as underline. And in between, there's a volume, there's space, and this space enclosed between these two surfaces constitutes the particular solid body, which has to fulfill some physical properties. And we achieve these two surfaces by performing deformation, by offsetting the input surface. So this is basically quite a simple mathematical operation. So for each vertex xi on the original surface, we define a vector vi and an individual offset delta I. And in this way, we can offset the vertex, and we get the vertex xi underline. And if we do it for all vertices and for in both directions, we achieve this offset. So far, this is not very much complicated. So the first problem is about the offset bound. So how far can we offset? Obviously, if we offset too far, we encounter problems like these self-intersections, which would destroy the physical validity of the shape. right? So we can have local or global self-intersections which we would like to avoid. And we do that by computing a skeleton inside of the object. This is some approximation of a medial axis. And we do it by using so-called mean curvature flow algorithm, which iteratively smoothes the surface and until it shrinks to this skeleton like that. This is an algorithm from Andrea Tagliasacci. Works quite well and has an additional advantage, which also answers the second question. How do we get this vector field V for the offsets actually? So in which direction we would like to offset. And the good thing is, since we derived the skeleton from the original input surface, we have a one-to-one correspondence of the shrink vertices and the original vertices, and this gives us a very smooth vector field, which is even much better in our case than, for example, a normal vector field, because it's low frequency, it's much more smooth, so we don't have high frequency fluctuations in high detail regions of the shape. Okay, and what happens to the outside? Well, since we would like to preserve the shape, we allow only small displacements to the outside, and for this reason, we just extrapolate or extend this vector field by some fixed constant value, and such that we can move to the outer direction. However, this is not a restriction. We could use here also some other methods to extend it to the outside. So, and so far, we have now the components to formulate a shape optimization problem. So, basically, we formulate it as a classical nonlinear optimization problem when you have some objective function f as a function of the offset values delta, subject to some constraints. And we can formulate it as the objective value. Let's treat it as a black box. So the objective function f could be, for example, make the shape float, yeah? And subject to some constraints like keep upright orientation, and also box constraints like keep minimal thickness of the material and so on. And this is something we could plug into state-of-the-art numerical software, like, for example, MATLAB's fmincon. We can solve it, for example, with a quasi-Newton nonlinear solver, and basically it would work. However, there are a number of problems here. So first of all, we have n unknowns, or actually we have twice n of unknowns, where n is the number of vertices, because we look for particular offset value for each vertex, or even for two offset values if you go to the inner and to the outer surface. So it's a huge number. If you can imagine, when you have a mesh with a couple of thousands or 10,000s of vertices, you have also twice as many unknowns. So the problem is very, very big. So it scales very badly. That means for large meshes, it's basically unsolvable. And it's strongly undetermined. That means that we are looking only for few properties of the shape, but have a very large design space. So that means that there exists a lot of good and bad local minima. So this is not very practical, and this doesn't work. Even on small meshes, it takes hours. So we came up with a first step, with a first solution for that problem, which we called order reduction. That means basically that we lower the dimensionality of the problem, but we try to preserve its input and output behavior. And here, the idea is to project it on some lower dimensional space. This is basically a sort of reparametrization, or finding a better parametrization of the problem. And here we came up with manifold harmonics. So manifold harmonics is a term which has been used by a couple of researchers in computer graphics. Basically, those manifold harmonics are the frequencies of the shape. If we look at the shape as a signal, we can decompose it into its particular frequencies, and each of those with an increasing frequency gives us some sort of basis function. So what I mean here is, when you look at after the decomposition of the signal, when you look at the first eigenfunction, or the first constant first frequency, it's a constant factor. So this is the DC component basically. And when you add on top of it additional basis functions, you see that they are starting getting spatially varying. So they are not more constant anymore. And when you add a number of them, a particular number, usually not a big number, then you obtain some freedom in design where you can offset, you can vary the offset, spatially vary the offset, but still you have only a few variables. So how to obtain those manifold harmonics? So we know that we have an input mesh, which is a polygonal mesh, and we can apply it in a discrete differential operator, the Laplacian operator, and construct the so-called Laplacian matrix of the mesh. And the eigenvalue decomposition of this matrix gives us basically the so-called eigenfunctions, or the modes, the frequencies, and so the eigenvalues are the particular frequencies, and the eigenvectors are discrete eigenfunctions. So this is some sort of generalization of Fourier transform, and if you know spherical harmonics, this is a generalization of spherical harmonics to arbitrary shapes. So now we having these basis functions, we can use them to reparameterize the problem. So now we are looking for a linear combination of those functions, and what we try to find or determine are the coefficients of these linear combinations. So basically, if you look at this equation here, this is the original displacement equation for each particular vertex, where we had this displacement value delta, and now we express each delta as a linear combination of those gamma ij, and gamma ij are these global eigenfunctions, and we are looking now for those coefficients alpha j. So basically now we have only so many unknowns as basis functions we are using, and in practice it has turned out that we need only a low number of them, and I mean really low. So this is much smaller than n. So usually it's less than 100, or in some meshes it's even in the magnitude of 10. So this is we're looking then only for very few unknowns, and using this we can formulate the optimization problem again. But using this coefficients alpha as unknowns, and this has also turned out to have a number of additional benefits. First of all, since we are taking only the low frequency components, we only displace and deform the low frequencies of the shape. So we don't change fine details on the shape. We change only like this global low frequency properties, which do not influence the visual quality or the general quality or the impression of the shape. So it's like only blowing it up or shrinking it, and it's not so much noticeable. Additionally, there are also other benefits. Like, first of all, we are independent of the mesh resolution. Because we have to solve the eigenvalue decomposition, but this is a sparse matrix, and we can use sparse methods where we can aim only for a certain number of k eigenvalues and eigenvectors. So this is using today's numerical software very efficient. This is a numerically stable operation because this manifold harmonics is orthogonal space, so we are transforming an orthogonal space into another orthogonal, so we avoid a lot of numerical issues. It is an implicit regularizer. This is already what I meant. Since we are using only few of them, the design space is regularized. It's smaller, and the minima which lie in this design space are only usually the good ones, the ones we are looking for. And last but not least, this whole algorithm is basically quite easy to implement. So example MATLAB code is on our homepage. So using this method, we have optimized mass properties. Mass properties are how the mass distribution within the object, which can be in fact computed as a function of the surface only using the Gaussian divergence theorem. So we don't have to discretize, in this case, the whole structure. We just use these two surfaces. And yeah, using this, we have created some, here we have optimized the axis of rotation for this turtle. This is another simple example is such a roly-poly bunny, where such a stand-up toy, where just the center of mass must be shifted up, actually below the center of rotation of the sphere this toy is standing on. And finally, we did some funny experiment. So we have created this tilted bottle, and it has been optimized. And when you fill it up with ethanol, which is basically alcohol, it stands. However, when you use it and fill it up with water, what happens then? Well, then the bottle topples because of the heavier weight of water. So this is a bottle you could basically check the amount of alcohol in your drink in your pub, right? Okay, so it was just fun. It was only to show how precise we can control mass properties of objects. So, and since it worked very well, so that was SIGGRAPH paper 2015. And since it worked quite well, we have investigated this problem further, and we came up with a unified framework where we tried to extend it or generalize it for more applications, not only for mass properties, but also for natural frequencies. So this is the sound of the object. If you hit it, the object vibrates, and this vibration basically constitutes the sound it exhibits. And when you can control the vibration modes, you can control the sound. And we have also looked at some structural strength problems. So how much load can bear an object, and can we optimize also such properties. And we came up with a more generalized solution with some improvements. And this is basically our final shape optimization pipeline, where first we have, of course, the input shape. The output shape is again a polygonal mesh. Now it's displaced. And in between we have those three steps we have seen so far. So we the parameterization with manifold harmonics. Then optimization, the definition of the shape properties, and then optimization of those. Now we have added material into that, so even more physical properties. We haven't, basically we also needed material for the optimization of mass properties, but since we assumed a uniform distribution of mass, you only need one constant mass density parameter, so this is very easy. If we work now with more complex physical problems, we need a proper or a more extended model of the actual material. Of course, we have some high-level user goals. So, what should this particular shape do or perform. And we have added yet another improvement to this whole pipeline and into this optimization, which we call local subspace projection. So this is which I will explain you in more detail next. Yes. So now, excuse me. Let us look at this shape optimization problem now from a little bit more general point of view. So phi I is now just a property. So the property might be its weight, its rotational axis, or some certain vibrational frequency. So there might be different properties. We want to look at them more generally, and this is just a simplified representation. It's a function. It must not be convex. It's definitely usually nonlinear in the parameters of the shape. So as denotes now the parameterization of the shape, it could be manifold harmonics as shown before. And then we have some desired user goal. So where, which particular value should the property have? So, and this is what we can formulate now as just a sum of squared differences of the goal value and the particular shape property we are trying to optimize. And this basically boils down to this general objective function where we just sum over those k properties we want to optimize. What does it mean, k properties? That means, for example, we want to optimize the position of the center of mass, the rotational axis. So the position, it's like it's a point. It's already 3 values, and also the rotational axis. Or we want to optimize for a number of frequencies. So not only the pitch, so the main frequency, but as you can imagine, if you want to have a nice sound, usually there is not only the pitch, but also the overtones, which give you the, I don't know in English actually, Klangfarbe. So the actual more a finer tone, which sounds just better for the ear. So you have to optimize not only the main pitch, but also the overtones. So that could be, for example, those k properties we want to optimize. And so we have this formulation, and let's maybe try to imagine the design space now. So we have like this m-dimensional design space. M now denotes the number of parameters, so the number of basis functions, like for example the number of those manifold harmonics we want to use, and so the number of alphas, and k is the number of the properties we want to optimize. And usually here again we have so this k is not the same k as I was talking about before. This k now means number of properties, and m is now the number of the basis functions, the alphas. And usually the number of properties is quite low, less than 10, and the design parameters are still, usually we need still a higher number of them. Why? We have figured out if we take too few design parameters, then we usually end up in long optimization times and usually end up with some bad local minima. So it has just empirically has turned out when you take a higher number of design parameters, we find better local minima. However, still we have the problem that this is a computationally expensive task. So we can compute the gradient of this objective function usually, and we have to evaluate it in every iteration of the minimizers of the quasi-Newton solver. And this altogether is still quite expensive. So we came up with some So the problem is solvable, you can solve it, but there are a number of disadvantages. So this is high dimensional, still underdetermined. We have to usually, we don't know the initial values, and the solution very often, or almost always depends on the good or bad initial value. There are bad local minima, so the shape is, the optimizer is long, and we cannot reach the particular goal target values, and the evaluation of the gradient is usually also expensive. This is also because in this case, when we optimize for sound, we have to discretize the shape now with finite elements. So we have also a large number of variables. So it's still, so it is solvable, but it's not well suitable for practice. And here we came up with an idea which we call subspace projection. And the idea is to project the problem again to a lower dimensional space, but only locally, and project it to as low dimensional space as possible. So that means when we are looking for 4 frequencies of the shape, let's project it to a 4-dimensional space. So we reduce the dimensionality, and now we are looking for few parameters. We call them now beta or beta, and they are only now k of those betas. So k is the number of properties we want to optimize, and our idea was here to find this space based on the assumption that we want to decorrelate the influence of the parameters beta on the particular properties. So that's related to local preconditioning or to preconditioning in optimization. It's not exactly the same because it's much more specialized. But let us have a look at what I mean. Maybe this figure will help us or help me to explain it. So what we are doing basically is to find again a local subspace where the parameters which we are looking for, the parameters beta, influence the particular, so this surface is, let's say the surface is the objective function, and we want to find a local reparameterization where each beta influences only one property. Okay, because in this original space we have seen that, for example, if you want to change the pitch of an object, we have observed that we have to adjust a number of those parameters alpha. And we thought maybe it's better just to map it directly. So let's find a beta which changes the pitch, and only other beta 1 changes only the pitch, beta 2 changes only the second overtone, and beta 3 should change the third overtone, and so on. So we have this mapping from parameters to properties more directly. So we want to decorrelate it, and this can be achieved if we solve locally and list a norm problem. So this is again, this is an underdetermined problem, so we have to solve a least norm problem such that this Jacobian here, so of key is now the parameterization, and phi is the vector of properties, and we are looking for mapping beta additionally that this whole expression is an identity. So this is basically what I tried to explain here, so that each parameter influences the only one property. And if this is the identity, then all other parameters, if you map it to this space, are tangent to the level set, and this level set, this black line, is the actual level set of the function. So they are tangent to the level set for this particular property phi 1. I can show now only one. If I want to try to depict it, And so all the others are tangent, and only beta 1 changes its value. And this results basically that the whole gradient, or the whole Jacobian, if you derive it in this space, is identity. And in fact, it turned out to work pretty well, but only locally. You can do it only locally, and this is an affine mapping, so or a linear mapping. And we have a nonlinear space. So what to do? Just apply it multiple times. So what we do is just linearize it locally. So we start at some position f of alpha 0 in the high dimensional design space, and then we find this map B, this projection, and project on it. So basically that means that we just reduce this dimensionality. Of course, we have to imagine we're working usually here in much higher dimensions. And I try to depict it now on this example with this surface and the line. So basically what we do is we project this problem onto the line and solve it in this lower dimensional space. So we're looking here for the next minimum we find, but only in this one, or this lower dimensional space. And we move in this space either until we reach local minimum, or when this whole expression is no more diagonally dominant, because it equals identity only at the point where we compute it. And as soon as we move, this whole expression is starting getting off no more identity. So it gets in different values on the off diagonal, and because we have to evaluate it every time. So the problem is now to either to reach a local minimum, or, and this is what we check each time, how diagonally dominant the matrix is. And as soon as it's starting losing the diagonal dominance, we just repeat it. So we are looking for a new local map B, find a new direction, move again along until, in this picture, I always go to the local minimum of this function, but it's not necessarily true. So if the map, the projection is no more diagonally dominant, we stop, and then again, and we repeat it until it converges to some local minimum of the higher dimensional design space. So this is like locally reprojecting it just by this linear map. And it has a big advantage that in each iteration, the whole gradient needs to be evaluated only with respect to the parameters beta, which are much fewer, only usually by 4 frequencies, 4 of them. So the whole gradient evaluation is much faster. And so the entire algorithm works like that. We find this space of alphas, for example, manifold harmonics. So we reduce the number of vertices only to a couple of alphas. Then we find a local subspace of those betas, then optimize this subspace. And as long as it does not approximate this alpha function very well, we recompute this local subspace and optimize again there and repeat it until convergence. So, and using this shape optimization pipeline, we have computed, for example, this toy animal Glockenspiel. So as input, we just took 2D shapes, these 2D profiles of those animals. We triangulated them, and then we computed this spatially varying thickness for each of these stones in order to achieve a nice spectrum where we optimize for 4 frequencies. So the goal was to find a pitch and 3 overtones. if you can imagine, when you're looking only for the pitch, all you have to do is just change the thickness, the constant factor of the thickness down. So this would be a very simple problem. But as soon as you start looking for more properties, so the shape should fulfill more than just the pitch, the problem is getting much more complex. So, and then we fabricated those stones using this milling machine from aluminum, and now we can see if we have sound, but we don't. Oh, well, it doesn't work. Yes, maybe I can show it to you offline then, after the presentation. It's a pity because they sound really nice, actually. So you have to believe me now. I will show it later to you. Oh, there's no way now for
try to change the stone settings if you want.
How about time? How much time do I still have? Like 10 minutes?
Yeah. Okay.
Repeat. Okay.
And then you have to sing.
Yeah, that's what I would. That would be a backup solution. No. Okay. Let's have a look at it later. So it worked well. I accepted it for SIGGRAPH 16 then. And then this is some measurements, and here you can see we compared the optimization of the particular so for this particular stones, so the blue lines is the objective value, how the objective value changes over time, so we let it run, and so how it decreases, and the orange one are our algorithm, and you see those steps is always a switch of the local subspace. So this is where a new subspace is found, and you can see in here in all cases in this example we converge much faster, and we converge to much better objective value. So even here is 10 to minus 2. So this is a sum of squared differences. So 0 is the absolute minimum. And yes, so this is this comparison to when we would optimize it in the full design space. But still, you see that it takes minutes, so it's not that fast. However, for example, this is because we have to discretize those objects with finite elements, and it's getting quite expensive in this case. In the case of the shape properties, which we have then also performed with subspace projection, we decreased the computation time very significantly, such that it could have been done in sometimes even less than a second, or in a range of seconds. So another example we have done is this optimization of structural strength. So when you 3D print an object with a constant wall thickness, you could apply some force on top of it, and depending on the force, it will withstand it up until some certain value of the force. So we have pre-computed the Van Mises force structural values for this object, and it resulted in that the object will yield, so it will break at this point. And then we optimize the object to withstand twice the force. So we want that the object withstands twice the same force, and we want to minimize the volume, so the usage of material. So we want to have it still as thin as possible. And the result was that our algorithm has thickened the object here and in those regions, and the simulation showed that it will yield at this point. So it will break at this point with twice as much force. And then we just tested it on a machine, on a professional testing machine, and indeed it turned out that this object yielded here at a value of about 1,000 newtons. And then we compared it to our optimized result, and indeed it yielded here, and of course also here, but first it yielded here, and a value of about 2,000 newtons. So it turned out to be quite accurate. All right, let me come to some limitations. Of course, everything has limitations. So first of all, the parameterization with manifold harmonics has, or generally with the offset surfaces, has the main limitation that if we are using the skeleton as an upper bound of the offset, we can never reach, for example, from this point, any point above there. So there is a limit of how much we can change the shape in the interior. And also in the exterior, it's always the question, when do you reach the self-intersection? So I told you we usually just try to have a constant to the outside, just because we don't want to change the shape too much. But this is definitely some sort of limitation. An alternative approach would be to use some voxelization here inside and to switch on or switch off voxels if you want to change the mass properties. This has been done in a concurrent work by Moritz Becher. So this is and also another limitation is that the computation of a skeleton is numerically not an easy task. It's messy. So that on the end it turned out that this what was the weakest point, the computation of the skeleton. So limitations of the subspace projection was, first of all, it's not like it always converges to I didn't mention it with these charts. So what you see here basically are different runs of the algorithm with different initial values. Okay, I have mentioned it before. So each of those lines, there are always two corresponding lines to each other, a blue one and an orange one. Orange one is ours, blue one is the standard optimization. And we always let both start from some random initial value. So that was actually why we see here so many of those lines. And it works very, very often, but it doesn't work always. So there are always cases we have encountered where we don't have an improvement. So you can't say that we are here definitely much better in terms of the optimization time and also the value of the objective function. So in these cases, we don't have much runtime improvements, and we haven't looked further into the numerics and what happens when the gradient matrix, the Jacobian matrix, is run efficient. So yes, to sum up, there's one story I didn't tell you. Maybe I can mention it now. So first of all, so we have presented this unified framework for shape optimization. We have introduced this parameterization with manifold harmonics, which turned out to be very nice in those cases. Even if they have a global support over the shape, they are derived from the shape. And in these low frequency regions, they turned out to be very well for this low frequency deformation. So they don't change the shape too much. We have introduced this efficient optimization with local subspace projections. And yeah, last but not least, it's quite easy to implement. And we have, for both algorithms, we have MATLAB code, example MATLAB code on our homepage. And what I haven't mentioned yet, they are not really coupled. So one can use the subspace projection also with other parameterizations. So we have also shown in our paper that you can use various parameterization, like cages over the shape or some radial bump functions and so on. So they are not restricted to each other. So the subspace projection algorithm works also with other shape parameterizations. All right. So yeah, that is my last slide. So thank you for the for listening, and now I open questions.
Questions?
Questions.
So I noticed you're not doing any deep learning.
I try to circumvent it. I don't know how long one can stand it, but no, I mean, we are not doing deep learning. No.
Yeah, you mentioned the skeleton dependency. That was one of the questions I had. Do you think about something different than using maybe virtual or
yeah,
basically?
I mean, to be honest, it turned out to be really the weakest or the, let's say, most part of the pipeline, because computation of a medial axis on 2D shapes is actually a mess. There are still algorithms, people still developing better algorithms for some medial surfaces or so on and so forth, but it's numerically difficult. And we struggled a lot. We tried a couple of algorithms, and we end up with this mean curvature flow, because it also delivered us the vector field. So because it was this shrinkage of the original mesh, we got these connections of original vertices and the vertices on this medial surface, and this vector field turned out to be very smooth.
The vector field depends on the skeleton. That limits the solution.
Pardon?
I said the vector field that you get from the skeleton limits the solution.
Yes, yes, absolutely. Yes. So I think you're right. I mean, I think this is the weakest point of this pipeline, and I think one could improve it. I think there is space for improvement. One possibility we were thinking of is to combine it somehow with the voxelization of the space, or maybe the computation of some smooth field. But then we have to discretize the space, and then you end up with voxels again, and it has another disadvantages. But definitely, I think there is room for improvements. Yes, but the vector field is discrete, but we have per vertex one vector, and it's fine. But in the case where you have to discretize the space and then compute a global function on it, like a Laplacian or something like that, that could be definitely tried and done. We haven't followed that actually, but I think it is possible to improve it.
Can you mention what the basis functions are?
What the basis functions are? Well, I mean, basically, we take the Laplacian of the mesh and compute the eigenvalue decomposition. And
the basis functions.
The basis functions are the eigenvectors. So the eigenvectors are basically, they represent the eigenfunctions. If you look at it in a continuous manner, that would be the eigenfunctions. So this is the interesting thing, that the diagonalization or the eigenvalue decomposition of the Laplacian operator is the Fourier transform of this shape. So, and these basis functions are just the eigenvectors sorted in decreasing order of the eigenvalues, and so on. So the first one is constant, and then you get, with increasing frequency, more and more fluctuations in that. So they call it also Laplacian. There are a couple of papers who call them manifold harmonics, and we also took this term, but basically these are Laplacian eigenfunctions, the shape, which are now also still an interesting intrinsic representation of the shape, and there are still new papers appearing which try to use this interesting shape decomposition. So the good thing is, if you take a Laplacian operator which is geometrically shape dependent. So it also takes the angles of the triangles and so on into account. So this is the cotangent Laplacian matrix. It's the eigenfunctions are coupled to the geometry. So they develop bumps there at some regions of the shape where you would need them, right? So that's why the linear combination of the offsets of these functions fits so well the original object. So that turned out to be good. The disadvantages might be that they are global. So usually each function changes the shape somewhere globally. But since we only used some low frequencies of them, so only a small number of them, it didn't. I mean, probably it's even an advantage. So, I mean, you could use, for example, some radial bump functions as well, which are much more localized. Radial basis functions, or maybe even splines, B-splines, or so on. Would still work.
More questions?
Yeah, I'm sure you have thought about possible applications of your methods. So if you go to automotive industry where you want to, I don't know, have a bumper that you did pedestrian or musical instruments or whatever, have you thought about that?
Yes,
or are there collaborators?
Actually, it's an interesting question because I mean, of course, you could use it, for example, for some as a toy tools optimization. I mean, our goal, I mean, this is a basic research project. So our goal is usually we want to explore this currently interesting direction of digital fabrication. How far can we go? How can we improve it? Our goal was here to, I call it consumer level, because those are algorithms which basically could be included quite easily, actually included into standard software. For example, this optimization of mask properties could be easily, actually we tried to implement it as a plugin for Blender, and I did a bachelor thesis about that, and the student implemented it. The problem is you need a library for the computation of eigenvalues, of sparse eigenvalues, and Blender community didn't want us to add some additional libraries. That's why we couldn't release it to the public Blender version. However, we have a local Blender version where we have integrated that. But I think it could be also now done. Now I'm working a lot with Rhino and with Grasshopper as a plugin for optimization of geometry, and I think it would be even easier to make a Rhino Grasshopper plugin for that, such that designers, I mean, this is our goal, designers, such that they can check on the fly if their object is plausible, for example, something like that. Yes, and there have been one project of FH Technikum Wien with some automotive company, and they contacted me if they can use it. And since I have released it as GPL code, so I said, yeah, sure, you can use it. I don't know if they have for
Okay, thanks.
Questions?
Yeah, so the code is available, MATLAB code. There's an example you can run in MATLAB, and usually, I hope it should deliver you some result.
Okay, there are no more questions, then thank you.
Thank you.
Next speaker in January is Holger.